Welcome back. So let's summarize what we have done so far in this playlist. So first of all, if you reach this point, congratulations. We cover a lot. I know it was a long playlist, but as you can see, we cover all RANS models that we have in OpenFOAM. We have many options. And we talk only about RANs. In the next CFD cookie, we're going to address URANs. Okay, so we're not going to cover the whole theory that, like in this case, just a few cases, because pretty much it's the same. The only thing that we have is time. Okay, and then I'm going to talk a little bit about numerical diffusion and what happens in URANs and what are the issues with URANs and what you should consider. Okay, but the theory, it is exactly the same. Coming back to RANS modeling, we cover all of these models, and let me go back to this list here where we cross all models that we have in OpenFOAM. We didn't cover these last two. These are related to transition modeling, and for this I would like to dedicate a specific CFD cookie playlist to address this. But to tell you in advance that these models, these two implemented in OpenFOAM, are based in the K-omega family, so they have the same properties that you will find here. And the K-omega SST is a 4-equation model. So besides the K-omega standard equations or K-omega SST, it is linked to 2 extra equations. The KKL omega, it is a 3 equation. So besides the K-omega, you have an extra equation. These two models are specific for transition to turbulence. So it is very difficult to capture. It's very elusive, and not everybody's dealing with this problem. So if you are dealing with these specific problems, there you have the models. As I say, it's very challenging. These are low rate. You need well resolvence meshes. There is no section, very fine meshes, very tricky to get converged. But that will be the issue of another video, another CFD cookie. So during this playlist, we address the question how to set boundary conditions in OpenFOAM, which sometimes can be a little bit confusing, a little bit difficult. Okay, instead, commercial software, everything is done automatically. We talk about also initial estimate, also limitations and recommendation for each model, numerics, how to change coefficients if you want to change the coefficients that you have in the model, and so on. Okay, so and to talk about that, it is very important to refer to the theory. You need to study a little bit the theory of each model. We address of each single model. We address now the paper used to implement it. So you don't need to reproduce the paper. You don't need to understand the whole theory. Just read. Just briefly review the paper, review the section related boundary conditions, related to limitations, a little bit equations, coefficients, and so on. Okay, so you are in a better position to choose which model to use, and if the results that you are getting are correct, or the assumptions that you are taking are correct. Okay, we also address the question, the question of how do I know if my simulation, my turbulent simulation, if correct, if I don't have validation data. So in this case, we have some validation data, but also we address that question, and we show now that all the theoretical values. So we have a very good theoretical background. To end this video, I would like to address another question that somebody asked me, and of all these models, which one is the best one? Which one should I use? And the answer to this question is a little bit candid, but yeah, I think, in my opinion, that is the only answer I can give you. The best model is the one that works for you, okay? All models will give you results. Some of them will have limitations, but it's the one that works for you today or tomorrow, or in this computer or in that computer, okay? The only thing that I can mention in particular with OpenFOAM is that stay away from this model, okay? We talk about this model, we talk that there is an issue that probably, in my case, in my experience, 80 or 90% of the time, it doesn't give me results. My assumption is the implementation of the boundary condition at the walls, but I need to study for that problem. But stay away from this, but for the rest, all models work. Have in mind that some models work only with full functions, okay? And some models, well, you have the hybrid treatment, so high, low rate, and so on. Some of them you have anisotropic behavior, and so on. So of this list, I would say, okay, that the best family of turbulence models that you have here is the K omega, with no doubt. Probably you already use these models. And of the K omega, particularly speaking, this is in my opinion, my personal choice. It is the K omega SST, K omega 2006. Of these two, I prefer K omega 2006. I have my own reasons. I don't want to discuss that, but as I say, that is up to you. All these models are okay. Then if you want to get out of the K omega, probably the spiral matters, and if you are working with, let's say, aerospace applications, airfoils, wings, and so on, spiral matter is fantastic, but it's not limited to that. To winds and turbo machinery. You can also use it for bluff bodies and so on. Or you can go with the K-epsilon traditional one, which use wall functions, or the ones with the low rate treatment. Okay, so it's up to you. Then you have probably from a mathematical point of view the most complete model, the most accurate one, which is the Reynolds stresses, or something in between eddy viscosity hypothesis, Reynolds stresses that can be, the B2A for the non-linear models or the algebraic models. So it's up to you to pick up one, but just to stress, I prefer K omega 2006. If I move to the K epsilon family, I will choose the Launder Charmer. It's a very good one, it's fantastic, I love it. Then also you have the Q zeta. We studied this one, which is, let's say, a sibling of this one, but with a manipulation. And what is interesting about this one, that by changing a coefficient, you can have an isotropic effect. If for you it's important anisotropic effect, I would say the B2F is a fantastic model. Not only an isotropic effect, but also if you move to Urans, this model tends to perform better. Okay, and then you will have the final models that are the Reynolds stresses. And here, well, I would say of these two, the best one is the LRR. So it is up to you. Pick up your model, validate it, understand everything. And at this point, I think I'm done with this playlist, with the runs. Just to stress, we study here runs. In the next one, we move to Urans. Only nothing changed. Remember, all boundary conditions, every is exactly the same. I'm just going to introduce how to deal with these unsteady simulations, statistics, and to address an issue that Urans, okay, it's difficult sometimes to capture, all the coherent structures. People wants to see all these vortices, so that is difficult. It's tricky to capture. We're going to see why is that. So at this point, thank you for your attention, and hopefully I will see you in the next playlist. Bye and enjoy.